So this is wave optics recording. Wave optics. Okay, we can talk about what is a wavefront. Wavefront is the locus of the line, locus of all points which are vibrating in the same phase. Locus of all the points which are vibrating in the same phase. So that's about wavefront and what are the different types of wavefront. Types of wavefront. Supposing there's a spherical source of light, the rays are going to emerge like this from it, and can imagine a spherical wavefront. These are the points at which they're vibrating in the same phase, and it's just kind of locus means a line joining, so that gives us a spherical wavefront. Next is a lines, source charge is a line charge. Obviously you will have a spherical wavefront. Okay, have a spherical a cylindrical wavefront. Point source of light will give rise to a spherical wavefront. A line source of light, this is point source of light, which gives rise to spherical wavefront, and a line source which gives rise to a cylindrical kind of wavefront, Next is a parallel beam of light will have plane wavefront. This is one wavefront, this is another wavefront. So these are the different wavefronts. You can convert one wavefront into another. How to convert one wavefront into another? Supposing you use place it in the principal focus of a concave mirror, the ray will get reflected back. Because it's the principal focus, it will emerge parallel to the principal axis, and thus a spherical wavefront get converted into a plane wavefront. Similarly, a parallel beam of light when falling on a concave mirror converge at the principal focus, which, as you all know, so the plane wavefront now gets converted into spherical wavefront. Similarly, you can also talk about a convex mirror in which a parallel beam of light will get diverged like this, and is going to appear to come from this point, and so then therefore you can say that a plane wavefront got converted into a reflected large spherical wavefronts. Can you see? This is reflected smaller wavefronts, these are reflected larger wavefronts. Can you see the difference between them? So if you use a lens, it's going to be refracted wavefront. A parallel beam of light is going to converge at the principal focus, so you'll get a refracted wavefront. From a plane wavefront, you're able to convert into refracted spherical wavefront. So then you can go on saying like this. You can use a concave lens. Concave lens is a diverging lens. A parallel beam of light is going to diverge after refraction. It's going to appear to come from a point here. Thus, a plane wavefront would have become, after refraction, huge spherical wavefronts. And so thus you can convert. You can also tilt wavefront. Say, supposing wavefront. Okay, supposing you have the wave coming like this, it's going to get bent towards the normal, and it'll get, when it comes out, it'll get tilted. So that's how you can tilt a wavefront like that when it passes through a prism. So that's about it. This is the introduction of this wavefronts. And next is the lesson starts with the most important, which is Huygens principle. Huygens principle. Huygens is the scientist name, is principle. According to Huygens principle, there are these key points you have to say. You have to define what is a wavefront. Wavefront is the locus of all the points which are vibrating in the same phase, is known as wavefront. Just define that, and then say that each point on the wavefront acts as a source of secondary wavelets, acts as a source of disturbance known as secondary wavelets. So you understood what are wavelets. Wavelets are the disturbances that are emerging from the primary wavefront. And the next thing is you can talk about the secondary wavelets spread out in all directions with the speed of light. These wavelets, secondary wavelets, travel and spread out with the speed of light. With the speed of light. Sorry about my bad handling, just bear with me. Let's go fast. Then you know that um, I'm telling you that supposing there's a wavefront, this is a primary wavefront. Every point on this wavefront is going to access a disturbance of known as secondary wavelets. Okay, an enclosure drawn to these secondary wavelets are known as secondary wavefront. Secondary wavefront, and these are nothing but secondary wavelets. These are known as secondary wavelets, and this is the primary wavefront. So these are the points, and the new wavefront is nothing but, can you see, secondary wavefront is nothing but an enclosure drawn to the secondary wavelets. So the 4 points very important. What are wavefront? The locus of the line, locus of the points which are vibrating in the same phase. Each point on the wavefront acts as source of a secondary disturbance known as secondary wavelets. The secondary wavelets travel and spread out with the speed of light, and the enclosure drawn to the secondary wavelets is called the secondary wavefront. These are the key points you have to talk about Huygens principle, and that's about stating whatever I've done is just stated the principle. Okay, but actually speaking, if you have to elaborate on it, you have to write like this. Take a point source of light. The light emerges, the ray of light emerges like this, and you're going to draw a primary wavefront which is basically perpendicular to the ray. And that's another point you can say, that the wavefront is always normal to the ray of light. This is another point you can include. And so then you draw a wavefront which is a primary wavefront. Every point on the primary wavefront acts as a source of disturbance known as secondary wavelets. An enclosure drawn to these secondary wavelets is called secondary wavefront. So the purple color is called secondary wavefront. The black color disturbance is known as wavelets. You can say wavelets or secondary wavelets, whatever. These are primary wavefront. Okay, and can you see at any instant of time t, if supposing it's traveling in vacuum, then the velocity is c, then the distance moved by it will be c into t, because velocity is distance by time, distance is velocity into time, which is c into t. So that's the distance traveled by it at any instant is ct. And you can see that this is the way you have to draw. Consider a spherical wavefront moving towards the right. So we are talking about the wavefront which is moving towards the right. Okay. Let AB be its position at any instant of time, which we are referring to as the primary wavefront. The region, see, the progression of light happens only towards the right and is not progressing towards the left. I'll come back to it next. So this is about explanation of spherical wavefront and how it progresses. And let's talk about a plane wavefront. Parallel beam of light produces a plane wavefront, and every point on this plane wavefront acts as a source of secondary wavelets, and an enclosure drawn to the secondary wavelets forms a secondary wavefront. As usual, you can write this as primary wavefront, secondary wavefront, and these are the disturbances known as wavelets, and at any instant again it will travel through a distance of ct or c into delta t for a small gap of delta t. However you want to write, you can write. And the progression is happening only forward. Backward propagation of the wave is not possible. You can name this as AB is the incident initial wavefront, and after a time delta t it progresses to CD as a spherical wavefront and CD here as a plane wavefront. So these are the diagram, which is self-explanatory. When you write like this and draw like this, you'll get the marks. So write a note on Huygens principle is the 5 points, and then explain spherical wavefront and a plane wavefront's progression. You also explain why the progression does not happen backwards. The backward propagation of the wavelets is not possible because it's simply just this, that the amplitude is directly proportional to 1 plus cos theta, and when theta is equal to 180, 1 minus 1 is 0, amplitude becomes 0, and that gives you an explanation as to why only forward propagation of the wave is possible. Energy travels only forward. Okay, so that's about it. Next is laws of reflection and refraction. Okay, now using Huygens principle, very very important question. Laws of reflection Refraction will come to it later. So let's talk about reflection using Huygens principle. Let's xy be the mirror because we're going to talk about reflection here. Let the incident ray be, this be the incident rays, ZA and Z dash B. Let's say this point is B. Let ZA and Z dash B be the incident ray parallel to each other. And so then this, you need an incident wavefront here. So draw an AB. That will give you your incident wavefront. Let AB be the incident wavefront. Okay. By the time, okay, now you have to reflect these points AB. Let's call it as C. By the time A goes here, then this also goes here. Okay. So then this is P and P dash if you want. Okay, so thus you need a reflected wavefront, so you can join this and draw a normal. Thus you got AB and CD to be the incident wavefront. Let AB be the incident wavefront. Let CD be the reflected wavefront. You know from here what you observe by the time, let me write by the time. A is reach the mirror. A is touch the mirror. B is still in air. Did you notice that B is still in air? By the time A travels to D, B reaches C. B reaches C. Therefore, you understand the time taken. Therefore, you understand the time taken for AD. Time taken to travel AD is the same as time taken to travel to BC. Yeah, and so since the time is the same and it's the same medium, it's only air or still vacuum. It's getting reflected back to where the velocity is just C. You can take it as C. So you know the velocity is C. So the distance traveled by AD will be CT, and the distance traveled by BC will also be CT, and therefore you can write AD is equal to BC. And you also know AC is equal to AC is the common hypotenuse, and an angle ABC is the same as angle ADC, which is 90 degree. Hence by RHS congruency, the two triangles are similar, two triangles are congruent. That is, the triangle ABC is congruent to triangle ADC, since the two triangles are congruent. So coming back here, what you should do is you should do a normal here at the point of incidence and mark this as angle of incidence. But we want what the angle of incidence the incident wavefront is making with the mirror. This is what is I. Similarly, you can do a normal at this point of reflection and now call this as R, but that's not what we want. We want reflected wavefront making with the mirror as R. Therefore, by congruency, you know angle I should be equal to angle R, which proves the laws of reflection of light. Laws of reflection of light says that angle of incidence equal to angle of reflection. That one law is done. And the second law is the incident wavefront, the reflected wavefront, and the normal all lie in the same plane. All lie in same plane. So these are the key points you must write, and this is about how you prove laws of reflection. Okay, so next is okay, in accordance with Huygens principle, from every point on AC, this point you can add, every point on this AC, secondary wavelet starts growing. So that's something you can include. Every point on AC, secondary wavelets, disturbances, secondary wavelets starts growing with the speed c. So that explains this point. Okay, during the time, the disturbance from by the time A reaches, disturbance from A would have traveled to D, B would have only touched C, and all those points. So this is enough. The explanation is enough to prove laws of reflection. Let's go to laws of refraction using Huygens principle, for which you have laws of refraction using Huygens principle. You obviously need a medium of separation, which is xy. It's not a mirror, it's a medium of separation in which you have an incident ray which is coming like this, two parallel beam of incident ray coming as usual ZA and Z dash z dash b, but in this it's going to get refracted, so you draw a normal at the point of incidence and it's going to bend towards the normal. It's also going to bend towards the normal, and you need the incident wavefront. So this b is the incident wavefront and cd is the refracted wavefront. And as usual you mark it as angle I. What is angle? This is angle of incidence, so this wavefront is angle of incidence. This is angle of refraction, so this is angle of refraction. And here you can't prove congruency because the velocity, this is air and this is medium, which is denser. This is rarer and this is denser, and hence the velocity here is c and the velocity here is v. And you know definitely the time taken. By the time you can write the same explanations, and you can say by the time a would have traveled to d, b is still in air. By the time a touches the mirror, or not the mirror, the separation between the two medium, b is still in air. By the time a reaches d, b is reaching c. So time taken for AD is the same as time taken for BC, but however the distances are not the same because the CT for AD the distance is VT, because velocity for AD is A. Velocity is V because it's medium, and here it's CT, and they are not equal. So therefore what do we do is it's about laws of refraction, where refractive index is sin I by sin R. So go for it. What is sin I? Is opposite, which is BC, by hypotenuse, which is AC. And what is sin R? AD by hypotenuse is AC. AC get cancelled. BC by AD. What is BC? As you know, it's CT. From here you can see that the CT is what is BC, and this is AD as VT, and T get cancelled. Thus refractive index is velocity of light in vacuum by velocity of light in medium, which is exactly what Snell's law is. So that helps you to prove laws of refraction. Laws of refraction is nothing but Snell's law, which says the refractive index of the denser medium with regard to rarer medium is equal to speed of light in vacuum by speed of light in medium, or sin I by sin R. And also angle of reflection. The second point is angle of the incident ray, incident wavefront, refracted wavefront, and the normal. All of them lie in the same plane. So these are the key points you have tried in laws of refraction. And here again you can say every point on AC acts as a source of secondary disturbance, just like the secondary wavelets, but starts growing inside the medium with the speed v. It's not with the same, it's got a different speed. So this is how we explain laws of refraction using Huygens principle. So next is support, you can look through aurora, how they are bending different light rays and how they are converting one wavefront into another, which is in page number 10.5. And then let's go to next is about principle of superposition of waves. Principle of superposition, when a number of waves are traveling through, so I'm going to deal with principle of superposition of waves. Okay, when a number of waves are traveling through a medium, when they superimpose on each other, they all add up. The resultant displacement at any point at a given instant is equal to the vector sum of the displacement of the individual waves at that point. Okay, it's a vector sum. See, supposing this is y1 vector, this is y2 vector and y3 vector, the total displacement is y1 vector plus y2 vector plus y3 vector. So when a number of waves traveling through the medium, so there is a medium and a number of waves are traveling, they superimpose on each other, they all getting added on each other. The resultant displacement, which is this y, is a vector sum of the displacement of the individual vectors. Are you clear? That's what is laws of superposition. And let me explain one thing about this. You know that when a crust and a crust is going to meet, it's going to add up and give you a larger amplitude. But whereas when a crust and a trough is meeting, this is a crust and a trough is meeting, the resultant will be zero. The resultant wave will have zero amplitude. So that's something that you can understand, that when two waves, this wave and this wave, are superimposing, this wave and this wave are superimposing, what happens, and so on. So let's go to next, interference. The phenomenon of interference. When two light waves of same frequency, key point, okay, same frequency, having zero or constant phase difference, having 0 or constant phase difference. So it can either there's a constant phase difference, or it has to be with zero phase difference. It should have the same frequency. So example of this is called coherent sources. Coherent source, a light from coherent sources will always have same frequency, and it will have zero or constant phase difference. So interference is, we are so again superposition only. Interference is, this is a coherent source. Define a coherent source. A coherent source is one which emits lights of waves of same frequency having zero or constant phase difference. But interference is superposition of two light waves having same frequency or zero or constant phase difference is known as, and which will produce a pattern, which produces a pattern with maximas and minimas on the screen. Just make sure you write these notes when I say this. Which produces the maximas and minimas on the screen is known as interference of light. So let's talk about the conditions for constructive and destructive interference. Condition for constructive and destructive interference. First is, let's start with y1 is equal to a sine omega t, y2 is equal to b sine omega t plus phi. As you see here, I am taking something with a constant phase difference, not zero phase difference, because phi happens to be the phase difference here. So take these two waves and superimpose them. You get y is equal to y1 plus y2, which is nothing but, I hope it's recording. Okay, a sine omega t plus b sine omega t plus phi. So then expand this. So you get a sine omega t plus b sine omega t cos phi plus cos omega t sin phi. Now take the b inside. A sine omega t plus b sine omega t cos phi plus b cos omega t sin phi. Now you can take these two because you have sine omega t common in this. A plus b cos phi plus you write a cos omega t, which is here directly here, cos omega t, and write b sin phi, so that this like sine omega t something plus cos omega t something. So this you write this something as r cos theta. Okay, so that's sine omega t r cos theta plus cos omega t r sin theta. The advantage of writing these two to be r cos theta and r sin theta, I'll tell you now. You can take r common. Sine omega t cos theta plus cos omega t sin theta is sine omega t plus theta. Okay, thus r being the resultant amplitude, you get something like this. R being the resultant amplitude. Now it helps you to find R because you already know this is this and this is this. Take these two quantities, square it. So you get r square cos square theta, which is a square plus b square cos square phi plus 2ab cos phi. Similarly, take the what is on the right and square it. R square sin square theta, which is b square sin square phi. Add these two, you will get r square because cos square theta plus sin square theta is 1. So a square plus this and this will just become b square because cos square phi plus sin square phi is 1 plus 2ab cos phi. So r therefore is root of a square plus b square plus 2ab cos phi, which talks about the resultant amplitude. R is nothing but the resultant amplitude. What were the original amplitudes? The Kuti amplitudes were small a and small b. After they superimposed, they got a big wave with an amplitude with resultant r, which is root of a square plus b square plus 2ab cos phi. Now let's study this, okay? Let's take a rotational motion. Let's take this point. At this point phi will be 0. At this point phi will be pi, then this will be 2 pi, this will be 3 pi, this will be 4 pi, and this goes on till 2n pi because they're all even numbers. This goes on till 2n minus 1 into pi because they're all odd numbers. And let's study for this position, these two positions in particular. Let's study for the right side. Cos phi is 0, cos phi is cos 0, which is 1. So the resultant amplitude r for this position becomes root of a plus b the whole square, root and square get cancelled. R maximum will get to a plus b on substituting all these conditions. So substituting this condition, cos pi is minus 1, so r will become root of a minus b the whole square, and so r minimum is condition is a minus b, which occurs at these angles. So therefore you know that maxima occurs at when phi is equal to 2n pi, and minima occurs when phi is equal to 2n minus 1 into phi, and these are the two things you should understand. Therefore r maximum by r minimum is itself a plus b by a minus b. Okay, so now you know that you should also know intensity is square of amplitude. So you have a amplitude or square here. Can you see this one? which can be transcended to write intensity. So intensity I is equal to I1 plus I2 plus 2 root I1 root I2 cos phi, because intensity this is a square, which is I1, b square is I2, 2ab root I1 root I2 cos phi. So because intensity is square of amplitude, so you can also write this as root of I1 the whole square plus root of I2 the whole square plus 2 root I1 root I2 into cos phi. There are various ways in which it's, you know, that when the intensity is maximum is when maxima occurs, when the intensity is minimum when minima occurs. This is a condition 2n when pi is equal to n pi and phi is equal to n minus 1 into pi. So then therefore intensity maximum by intensity minimum can also be found by squaring this. So a plus b the whole square by a minus b the whole square. Numericals, as I told you, we can always take the b out, b square out, b square is taken out, a by b plus 1 the whole square by b square out, a by b minus 1 the whole square, b square get cancelled, in which if they give you the ratios of the incident amplitudes a and b, you can find the intensity maximum by intensity minimum using all this. Okay, there's another thing that I taught you is about slit width of windows. W1 by W2 is directly proportional to intensities I1 by I2. Okay, so then the slit width and intensity are directly proportional. Intensity and amplitude is square, correct? So then therefore it's a square by b square, and this relationship will help you to do a lot of numericals which I discussed in the class. Okay, so let's go to next. These are the conditions for conditions for constructive interference, constructive and destructive interference. Right side, whatever I've written, these are all the conditions for constructive and these are all the conditions for destructive. So that's about these conditions. They ask you write a note on interference. Next is about you know what is a coherent source of light. Coherent source is one which emits light of same frequency with zero or constant phase difference. I just explained it there also. In this whole experiment we are using only coherent source. Okay, so then for numericals I have put separate video. Now let's do Young's double slit experiment. YDSE, Young's double slit experiment. In this there is a slit here, double slit. Can you see the width of a slit is D, which is getting broken down to D by 2 and a D by 2. It's like taking a cardboard and putting two holes. These are very, very small holes from which light is getting emitted. You have to have a screen here, and as you can see from this end the light goes like this. From this end the light goes like this, and can you see that from this is slit 1 and this is slit S2, and just draw it into straight line also. When the light goes like this straight line, there's no path difference, so then that will result in maxima at the center, obviously. But when it goes to the other end P, it is on the, this is center, other end P, you can see that the path difference from S1P would have traveled lesser distance, whereas S2P would have traveled a longer distance, and hence there is a path difference, which is, this is the path difference delta x. This is the path difference, and that delta x is nothing but obviously S2P minus S1P. The whole objective is to first find the path difference. Okay, so first of all you should know that the distance between the slit and the screen is capital D, the width of the slit is small d, and half of slit is D by 2 and a D by 2. Therefore this end is D by 2, this end is D by 2. This is the central maxima, and the position P is at a point Y from the central maxima. Therefore this distance from here is Y minus D by 2, and the whole distance see, for the whole triangle it is Y plus D by 2. So then I'm going to take these two triangles, because I can't directly find S2P minus S1P. Rather I will take these two triangles. Can you see the triangle? I'm going to take a blue color triangle here, according to which I can find S2P, S1P square. S1P square is D square, which is base square, plus opposite, which is Y plus D by 2 the whole square, Y minus D by 2 the whole square. This point is Y minus D by 2, blue color, right? And let's do take the bigger triangle, which is here. Can you see the bigger triangle? And so from that you can write S2P square, which is D square minus Y plus D by 2 the whole square. In fact, that is the whole length for that triangle becomes Y plus D by 2 the whole square. Now I'm going to subtract S2P, second equation minus first equation. S2P square, when D square get cancelled, Y square, you expand this, you can imagine Y square, D square by 4, everything get cancelled. YD and YD will get added, so 2YD. Now just make sure that you're going to split it up into S2P plus S1P into S2P minus S1P, which will give you a 2YD. And the scientists, they just took the hypotenuse to be approximately equal to this, because the distance between the slit is, considering the slit and screen at a very far away distance, so they'll consider this as d and d is to 2d. But if you do the same thing here, it will become 0, the purpose will be lost. You have to find the path difference. So only there you have to assume it as 2d. So 2 and 2 get cancelled. So s2p minus s1p therefore gets you to y into small d by capital D. That's the path difference delta s is y into small d by capital D. This is the first part. The next part is going to get, you have to remember this, okay? You have to remember this, that, what should I say? We already know the condition. You're going to study the condition for maxima and minima. We have already studied the condition for maxima and minima. Let's write the maxima here. We know that phi has to be 2n pi from the previous derivation. The minima occurs when phi is 2n minus 1 into pi. We already know these conditions, right? So let's write like this, and take the right hand side and write these conditions. Put a box here and try to write. 2 pi is the phase difference when the path difference is lambda, which is common sense, right? Full wavelength is 2 pi when the path difference is lambda. What will be the path difference delta x for a phase difference of phi? You should write this statement and do the cross multiplication. So you get delta x is equal to lambda into phi by 2 pi. But for maxima, you know what is phi. So for maxima, delta x is going to become lambda into 2n pi by 2 pi, where 2 and 2 get cancelled, pi and pi get cancelled. Delta x itself is n lambda. For minima, you know delta x is equal to lambda into phi is 2n minus 1 into pi by 2 pi. Pi and pi get cancelled. Thus delta x is equal to 2n minus 1 by 2 into lambda. So this is for minima and this is for maxima. You just have to write these two, this other side, okay? So now that you know that for maxima, delta x has to be n lambda for maxima. You already know what is delta x from here, equated to y into small d by capital D. Therefore, yn is equal to n into lambda into capital D by small d. Y1 is equal to lambda into capital D by small d. Y2 is equal to 2 into lambda capital D by small d. Fringe with beta is equal to y2 minus y1, subtracting it lambda into capital D by small d. Thus, the fringe width formula is also lambda into capital D by small d. Y1 corresponds to first maxima. Y2 corresponds to second maxima, and so on, okay? For minima, as you know, the minima's condition is this. So when minima can occur between two maximas. You can even think of it like that. So your first minima will occur at, if this is 1 and this is 2, it will occur at 1.5. So 3 by 2 into lambda into capital D by small d, which is the first minima. Between two, you can even say that between two maximas is where the minima occur, and make it very, very simple. The second minima is 5 by 2 into lambda into capital D by small d. Second minima is occurring. These are the positions of minimas, and these are the positions for maximas. And you understand that interference pattern has got uniform intensity, which I want you to ask your teachers, how is it even possible? But according to the theory in the Aurora, the intensity versus the position, you know that the minima, this is the first minima, this is second minima, and you know it's 3 by 2 into lambda into capital D by small d, it's 5 by 2 into lambda into capital D by small d, and so on. Your first maxima occurs at lambda into capital D by small d. So these are the minima's position. I hope you understood. So when you put 2n minus 1 by 2 into lambda, in this condition you put n is equal to 1, you get lambda into capital D by small d. So in that condition, n is equal to 1 will give you 1 lambda 1 by 2 into lambda into, so this corresponds to 1 by 2, this corresponds to 3 by 2, this corresponds to 5 by 2, and so on, correct? The first minima occurs at, okay, so the first maxima on either side, this is the first maxima on either side, so we can say this is the maxima which is occurring at, see, it's not writing, 1 second, hold on. Okay, can you see this is the first, this is center from which the first maxima on the above, on the right side or above is occurring at lambda into capital D by small d, lambda into capital D by, makes sense to have a half here, right? So that's about it. This is this we call it the central maxima, but it's not wider or anything, because according to Aurora, all every fringe width is uniformly spaced. Uniform fringe width, perfectly bright and perfectly, each dark fringe is each bright fringe is perfectly bright and each dark fringe is perfectly dark. Okay, and then the intensity is uniform for every fringe, which is what I don't understand, but and these are the points which has been given, and these are the conditions for interference pattern. Okay, it's about Young's double slit experiment. Next is about after Young's double slit, it's diffraction. So what is diffraction? Is the bending of the light ray around the edges of the obstacle and forming a pattern in the geometrical shadow region is known as diffraction. Bending of the light ray around the geometrical obstacle, okay, bending of the light ray on the edges of the obstacle, thereby forming a pattern in the geometrical shadow region is known as diffraction. Make sure you write that definition for diffraction. And there are two types of diffraction. Two types of diffraction. One is a Fresnel's diffraction, next is a Fraunhofer's diffraction. Fresnel and Fraunhofer's, okay? Fresnel and Fraunhofer's diffraction. The difference being, in Fresnel diffraction, the source and the screen are placed close to each other. The source and screen are close to the aperture or obstacle, and the light after diffraction appears converging. So you can say they're close to each other, whereas in Fraunhofer's, they placed at a large distance. The source and the screen, the distance between the source and the screen are so far away in Fraunhofer's. So basically what we are doing is Fraunhofer's, because we always keep making sure that D is larger, right? So aren't we only doing Fraunhofer's diffraction? So then not Fresnel diffraction here. So what is that explanation I'm going to give for Fraunhofer's? Is it recording? Yes. So Fraunhofer's diffraction, you know that how I'm going to draw. Let's see. You have to have a source from which light is going like that. But I told you the source has to be at infinite distance for Fraunhofer's, and therefore I am using a convex lens so that the light ray will come parallel and it will appear that the source is at infinity. That solves my problem, right? It will appear that my source is at infinity, and you have a slit. It's only a single slit, it's not a double slit. You have a single slit diffraction. This is called single slit diffraction, in which this is a single slit, and you're going to use another convex lens because it's a parallel beam of light and it has to converge on the screen. The distance between the slit and the screen being capital D as usual, and the width of the slit being, we call it as A in this, we don't call it as D. In this diffraction we call it as A, and you know that a ray which is going straight will converge and fall on the screen because parallel beam of light, and will come to focus here. There's no path difference, hence you get a central maxima as usual. So O at this point, okay. But let's very clearly, you have to draw like this. From here, from this point, you have to draw a straight line like that, and then from here go there and converge it here. From here go here and converge it here. That drawing should be clear because it's taken straight, and this can be a theta and this is your y. The point P is above and the distance from center is y, and therefore you can write tan theta is equal to y by capital D. That is your inference. The next observation that you can do is you can just draw a wavefront, which is this, which is your incident wavefront, and you see this is also theta. In that case, this will be a path difference. As you know, this is a path difference, and you know that sine theta will be path difference by the slit width A, correct? Path difference by. So these are the two things that we are observing here. Let's continue to do the derivation. So that's about this. Supposing a parallel beam of light from a monochromatic source. So this source is a monochromatic source, which has single wavelength. Monochromatic source is incident on a narrow slit Ln of width A, the incident plane wavefront WW, that will, this will cause a plane wavefront which is WW dash, that will be the incident wavefront. Is now coming into it. The incident plane wavefront disturbs all path between Ln, and the secondary wavelets emerge from every point between L and N. And as you can see that there is a path difference because LP is short distance where NP is a longer distance. There is a path difference. The wavelets spread out on all directions, causing a diffraction of light. The diffraction pattern consists of a central bright band surrounded by alternatively dark and bright bands. Okay, so as seen in the diagram. Are you clear? So that's the notes, initial introductory notes that you have to write. And here comes the further explanation. Very, very important. Out of the blue, you're going to say that imagine the slit to be divided into two halves. There are two wavelets coming at a time. There is one wavelet on the first half and so exactly two wavelets coming into it. One wave, we are imagining in the entire process, we are imagining that the path difference between each wavelet is lambda by 2. Very, very important, between each wavelet is lambda by 2. So then what will happen? Here you have to write lambda by 2. Therefore here it will be lambda. This is your theta and this is your A. Can we take this will be therefore A by 2 and A by 2, or we can even call it as D by 2 and D by 2, it's your wish. So A by 2 and an A by 2. So take this triangle, you have sine theta is equal to opposite, which is lambda by 2 by A by 2. 2 and 2 get cancelled. A sine theta is equal to 1 lambda. You can even call it as D, okay, that's convenient for me. D sine theta is equal to 1 lambda. Okay, because this has a path difference of lambda by 2 initially, which means there's a crust and a trough which is meeting obviously. They both are going to cancel out. The resultant will be resulting in a minima, and this happens to be a condition for minima because the two wavelengths individually having a path difference of lambda by 2 is going to cancel off each other. So then the d sin theta is equal to 1 lambda is the condition for minima. So let's see, let's imagine the slit to be divided into 4 halves now. 4 halves, 1, 2, 3, 4 halves. So you know that each one has a path difference. This will be lambda by 2, this will be lambda, this will be 3 lambda by 2, this will be 2 lambda. So this slit width will be d by 4, this will be theta. Take this triangle, sin theta is equal to lambda by 2 by d by 4, where the 4 and 2 get cancelled, and will be d sin theta is equal to 2 lambda. Condition for minima again, second minima. So like that you can like this we can continue to consider the slit to be divided into even halves, HALVS, okay, even halves, where each having a path difference, each wavelet having a path difference of lambda by 2 superimpose, resulting in minima, because each wavelet is cancelling out each other. So I've explained the condition for minimum to be d sin theta is equal to 1 lambda, d sin theta is equal to 2 lambda, d sin theta is equal to 3 lambda. So d sin theta is equal to n lambda, considering that there are n even halves. Now consider the slit to be divided into odd halves. The wavelets coming out of it, each having a path difference of lambda by 2. This will be d by 3, and this is theta. Take this triangle, sin theta is equal to lambda by 2 by d by 3. So d sin theta is equal to 3 by 2 into lambda by small d. What am I writing? No, d I have taken it to that side. So 3 by 2 into lambda. Can you imagine between two minimas is where maxima. Here d sin theta is equal to 1 lambda, d sin theta is 2 lambda, so it has to be 1.5 lambda. So d sin theta will be 5 by 2 lambda. If you imagine the slit to be 5 halves, d sin theta will be 7 by 2 lambda. And so on. These are the conditions for maxima. Why is it maxima? Because when two wavelets cancel out each other, you still have the third wavelet still forming a maxima there. So that is the explanation you need to write for the maximas. So thus you got the conditions for minima and maxima. Okay. So now since you got the you must observe that n lambda was the condition in interference. It was for maximum. In diffraction, that turns out to be for minima. And for minima in interference was 2n minus 1 by 2 into lambda into capital D by small d. But here it's, you're going to consider this 2n plus 1 by 2 into lambda. Okay, the final answer 2n plus 1. Just make a note of it. Okay, there it's 2n minus 1, here it's 2n plus 1 by 2 into lambda. So then these are the key points for the diffractions, maximas and minimas. So what else I should say? But here I should d sine theta. Here n is equal to 1, 2, 3 and so on. Okay, there also it's 1, 2, 3 and so on. Okay. But here this is okay. Let's find out, figure out. The diagram has been given like this. The diagram is given like this, where the intensity is like this, and the fringe width is also reducing, and the intensity is also reducing. This is intensity versus position, and this position is the first minima's position. Minima is can you see? Okay, this is say in case I'm doing it for theta. It's not for the position, I'm doing it for theta. Sorry, this is between not position, I and theta. What is theta here? I get lambda by d, first minima. So lambda by d. So you know the first minima occurs at lambda by d, then it's 2 lambda by d, and then 3 lambda by d. If sometimes it can be even a, so minus lambda by d minus 2 lambda by d and so on. So this is the graph, and the intensities of the secondary maxima relating to intensity of, can you see that there is a big wide central maxima? Therefore from here you observe that there is a wide central maxima. The intensity of the first secondary maxima is just 4% of the central maxima. Okay, forget about this point, you don't need that point. So n is never equal to 0, okay, in all this. Okay, so that completes it. And so to explain what is the width of the central maxima, you know this position y1. What is this position y1? Which we already wrote. What is tan theta is y by d. You already know tan theta is y by d, y by capital D, correct? And what is sine theta? For the first minima is lambda by d. For the first minima is lambda by d, and we are approximately taking tan theta to be approximately equal to sine theta, and this is the condition I am observing for minima, and therefore y is equal to lambda into capital D by small d stands for this distance y, and so I have to double it in order to get this width of the central maxima. Width of central maxima therefore is double the thing, so 2 into lambda into capital D by small d becomes the width of the central maxima. And as you know, there is a big wide maxima at the center, with the intensities of the secondary maximas decreasing, and it's been given that it's a ratio 1 is to 1 by 21 is to 1 by 61 is to 1 by 121. The intensities of secondary maxima relating to the intensities of the central maxima are in the ratios like this. Okay, that's what has been given. So that's about it. This is write a note on diffraction. If they ask you, this is what you're going to write. Okay, that's it, guys. Then it's just the numericals.